All right. So we're going to get into the lab, and we should probably just do a little bit of review about pH and what a buffer is. So you're clear about what this is all about. So what is pH actually measuring?
Acidity and base.
So we say as things are more acid if the pH is lower, or more basic if the pH is higher. That still doesn't tell me what it's actually measuring.
The
Like,
number of
Something to do
hydrogen
with
ions.
hydrogen.
The number of
Yeah.
hydrogen ions.
Yeah, so this is a measure of hydrogen ion concentration. You know, there are other ways to think about what pH is. For our class, this is going to be how we're going to think about it. There's more subtlety to thinking about what pH is, but in general, pH is minus logarithm of the hydrogen ion molar concentration of hydrogen ions. So, and it actually is important to understand the basic little formula here. Plug in, or else I'm going to run out of juice. What does log mean in the mathematics?
It's a, I
Is
don't
it to
know.
the 10th power or
You're on the right track. So it's basically the inverse function of raising something to the 10th power. It's saying this is the number you would have to raise some 10 to get it back. So basically 10 to the log x equals x. It's saying, so the log of x is saying, what number do I have to raise 10 to give me x? So for instance, what would be log of 10? What power do I need to raise 10 to give me 10?
1.
1.
1, exactly. That'd be 1. If I had 10 to the minus 2, this is the same as 1/100th. If I said, what's the log of 10 to the minus 2?
100.
2.
It's not quite. What power do I have to raise 10 to give me 10 to the minus 2? What number do I have to put in this box if I want to end up with this whole thing being 10 to the minus 2?
100?
This is like who's buried in Grant's tomb.
Is it 10?
No.
10 times 10?
So
Point-
I
point
want
one?
the- okay, I want the answer to be 10 to the minus 2.
So the
I have-
answer to 10 to the minus 2 is 100, right?
No, so here, listen. I want my final answer to be 10 to the minus 2. So I want to know what number do I have to put in this box there if I want my final answer to look like that.
-2.
-2.
Did you really just say who's buried in Grant's tomb?
Yeah, like, that's another old joke, right? Who's
I
buried?
know, I like it.
But it's like, what power do you have to raise 10 to get you 10 to the minus 2? -2, right? So for the rest of our discussion of how pH behaves, though, it's important to have a sense of how log behaves, or else it doesn't make sense. It's also important to realize that log is nonlinear, right? If I have 10 or 100 or 1,000 or 1,000,000, This is basically 10 to the 1, 10 squared, 10 to the 3rd, 10 to the 6th, right? If I look at log of each of these, this is 1, 2, 3, this is 6. So each time the log increases by 1, the number that I'm doing is actually increasing by an order of magnitude. So if the log changes by 3, X is actually changing by 1,000, right? If the log changes by 6, X is actually changing by 1,000,000.
It's the Richter scale.
Yeah, exactly. The Richter scale is just like this. Exactly. Right. If you're on the Richter, if it's like, 3 on the Richter scale versus 5 on the Richter scale, that's 100 times worse having the 5 than having the 3, because it's 2 orders of magnitude. Those two notches is actually 2 or 10 to the 2 or 100. All right. So now we can say, so remember that pH is just minus log of hydrogen ion concentration. We'll come back to this. So let's talk about just distilled water. If we have water that's just H2O, and it's just sitting there in your glass of water, those H2Os are wiggling and jiggling and bashing into each other. And every once in a while, an H2O will break apart into an H plus and an OH minus. This is also a proton. Right? I could either say an H plus is a hydrogen ion, but since a hydrogen is just a proton and an electron, once it loses its electron, all that's left is a proton. So I will interchangeably say H plus or proton. Proton, hydrogen ion, it's the same as saying a dog and a canine or a pooch or something, right? There's no difference between a proton and an H plus. In reality, if we were in a chemistry class, we would get more complicated. We would say like H pluses don't actually be independent like that. They're going to have hydronium ions, which are more complicated, but don't worry about it. For our class, we are going to work with the oversimplification of just H pluses exist and follow them along. And then the other part left over, the OH minus, this we often call a hydroxyl. So every once in a while, an H plus breaks apart, just sitting in your glass of water on your bedside as you're kind of napping or whatever. And at the same time, these H pluses and OH minuses whack into each other and they recombine to become a water molecule once again. Right? So this is constantly happening. Some of them break apart, but then the ones that are broken apart get back together and recombine. And there's an equilibrium. And normally in a glass of distilled water, most of the water molecules are intact. And there's a few that are dissociated like this. H plus concentration in distilled water is about 10 to the minus 7th, basically moles of H pluses per liter, which 10 to the minus 7th, remember that's 10 to the minus 7th. This is the same as 1 over 10 with 7 zeros after it, or 1/10 millionth. So that's the molar concentration of H pluses, not that much. That's why I was saying distilled water is not very good at conducting electricity. Yes, there are a few charge carriers there, but not many, not enough to make a difference in terms of making the buzzer buzz in our experiment last class. So, but then we can plug this in to the pH formula. So what is the pH of distilled water? We just plug it in. Minus log of hydrogen ion concentration, 10 to the minus 7th. And we've already just done the little exercise. What power do you need to raise 10 to give you 10 to the minus 7th?
Minus 7.
Minus 7, exactly. And then there's a minus sign in front. So pH equals 7. That is why neutral, like just regular water sitting there, is a pH of 7. It's just a reflection that that's the concentration of the hydrogen ions in that water in equilibrium. Now we can talk about acids and bases. Let's start with acids. Strong acid versus a weak acid. Strong acid would be something like hydrochloric acid. So by strong acid, it's something that dissociates completely once you put it in water. So if I put hydrochloric acid into my water, there's all of a sudden a bunch of extra H pluses around that weren't there before. So now, when I had my distilled water, which was kind of going back and forth to H plus OH minus, but ultimately had a very low H plus, was around minus 7. What am I saying? Equals 10 to the minus 7. If I add this in, all of a sudden, I'm going to have lots of extra H pluses adding in. And so now, let's say I was 10 to the minus 4th instead. Right, 10 to the minus 4th is a lot. That's like 1,000 times bigger than 10 to the minus 7th, right? Every time my exponent goes up by 1, I am increasing by a power of 10. 10 to the minus 7th. This is 10 times more is 10 to the minus 6th. Times 10 again would be 10 to the minus 5th. Times 10 again. So this is 1,000 times as much hydrogen ions as I had in my distilled water. What is the pH now?
4.
pH is 4. So things to remember here. pH goes down as hydrogen ion concentration goes up. And acidity goes up. People get all confused because some things are going up, some things are going down. As the pH number goes down, because of the way the equation is written, that actually means that hydrogen ion concentration is increasing. So as H plus goes up, acidity goes up, but the pH number numerically goes down. A weak acid is something that does not dissociate completely. We'll come back to the weak acid in just a few moments when we talk about how buffers work. But the strong acid is pretty easy to understand here. You put in this thing that dissociates, adds in H pluses. As you add H plus into the mix, then this H plus concentration goes up, which means the pH is going down. That means we're becoming more acidic. A strong base is something that is going to be taking H pluses out. Typically, it's something that adds hydroxyls. So for instance, a strong base would be, for instance, sodium hydroxide, which dissociates completely into Na plus OH minus, that hydroxyl. But now if we think about our distilled water, the H2O, if I am now adding a bunch of this stuff into the mix, these OHs are going to be combining with the H pluses and becoming waters. So all of a sudden, we're going to have less H pluses than we had before, because these new OH minuses that are adding into the mix are removing H pluses. So if our distilled H2O was H plus was 10 to the minus 7th, which was pH equals 7, as we add in these OH minuses, take these out of the solution, maybe I'm gonna have an H plus concentration now is only 10, 10 to the minus 10th. That would be like 1,000 times less, right? I have lowered the exponent by 3. I have now 1,000 times less hydrogen ions concentration than I had before. What's the pH for this thing?
10.
It's 10. So this is going to mean more alkaline or basic. But it means less concentration of hydrogen ions. So again, so it's another thing where you want to keep things straight. pH goes up as hydrogen ion concentration goes down. You know, alkalinity is going up. You know, acidity is going down. This gets confusing. I promise there will be there'll be questions probably on your quiz, which is coming up next Tuesday, as well as on your first main exam, which is coming up in a few weeks, where you are going to have to make sure you keep this all straight in your head. So, you know, so review this, make sure that you've got a good sense of what pH is measuring, how the pH number changes as H plus goes up or down, how that affects these concepts we call acidity and alkalinity. Because again, these are going to be important concepts through the semester. So that all makes sense? So pH is something that you really need to control in your body. pH can be changed pretty dramatically. I mean, imagine, I don't know, let's just be silly here. And let's say there was one H plus here. And then I added in a drop that had 100 H pluses. All of a sudden the pH just went up, you know, down by 2. You know, it's all of a sudden it's 1,000 times more acidic. Not 1,000, 100 times more acidic. When the pH changes, that actually, we're going to talk about why on Thursday, that can denature proteins. Proteins are going to change their shape if the pH changes. If the proteins change their shape, what happens that we talked about? I mean, lots of things are going to go wrong, but what in particular, based on our talk about enzymes, is going to go wrong?
You can change a binding site.
Yeah, you're going to change the shape of the binding site. The enzyme can no longer bind its substrate, and the metabolic pathways aren't going to work anymore. So pH homeostasis typically it stays around 7.4. We're going to talk about lots of different ways your body has to achieve pH balance. It's going to involve your respiratory system, your urinary system. But the first line of defense against change in pH that keeps the pH stable here, so it's not going to change, so you're not going to mess up your proteins, is this idea of pH buffers, chemical buffers that stabilize pH. Resist changes in pH. So this is really important because there's lots of chemical reactions that are creating acids or creating bases, or depending what, you drink a thing of orange juice, you're taking a bunch of acid into your body. There's lots of things going on that are working to change the pH of your body fluids. So you need to make sure that whatever is going on gets counteracted to keep the pH here. So these chemical buffers work like this. For example, carbonic acid. So carbonic acid is H2CO3. This is a weak acid. So it dissociates. When you put this into water, it becomes H+, which is why it's an acid. And it has its associated anion, which in this case, it's a polyatomic one. It's CO3-. This is a bicarbonate ion. So it dissociates, but not all of it does. Some of it just stays intact as this. Some of it turns into this. And it can go the other way as well. So this is weak acid, means incomplete dissociation. Some of it breaks apart, some of it stays. So in the water right now, we have some of these things that are just floating around as H2CO3s, but other ones that have broken apart and created this. So let's see what happens now when we add in some strong acids or bases. Let's say I add in hydrochloric acid, which is going to start adding in extra H+. If I start increasing the amount of H+ in the water, those are going to start pushing the equilibrium this way. Right? If you remember, we have this idea of the concentration of the reactants and the products is part of what drives the reaction. If you start increasing a bunch of H+ over here, those are going to drive the reaction this way, and these extra H+ are going to be grabbing onto these bicarbonates, and they're going to get taken out of the system, and the pH is going to kind of stay more stable. The other possibility, if I added a strong base, and all of a sudden there's a lot more OH- around than there were before. Those OH- are going to be combining with the H+ and taking them out of solution and turning them into water. As we lower the amount of H+ on this side, more of this is going to dissociate and add them back in. So whichever way it happens, the equilibrium in this thing is going to shift to compensate. If we add more OHs here, the equilibrium shifts this way to add the H+ back in. If we have excess H+ on this side, the equilibrium goes this way and takes them out of solution and turns them into these carbonic acid. So we call it the bicarbonate buffer. So this is one of the main ways that your plasma stays stable. There are also phosphate buffer systems based on phosphoric acid. These are common inside your cells. Proteins can actually act as buffers. We're going to talk more about proteins are made with these amino acids, and the amino acids themselves, different aspects of the amino acids can act as a buffering agent. So you have a variety of things that will help stabilize, resist changes in pH. And these are really fast. Like pretty much instantly. These are going to be the first line of defense against changes in pH to maintain your pH homeostasis. Obviously, there's a limit, right? If I am working with H2CO3 in equilibrium with H plus HCO3 minus, there's a limit to how much this can adjust for because there's a limited amount of these different chemicals floating around in the water. So you could overwhelm the ability of this chemical buffer to do the job. So there's going to be other mechanisms waiting in the wings to also help with pH balance. But in terms of the first fastest line of defense, these buffer systems are indispensable. And I should mention there's a more complete description of the chemical equilibrium. There's the weak acid and its conjugate base. But for an intuitive sense of how they work, you can just think about it like this. Think about an equilibrium with this weak acid either going in one direction or the other. So any questions about that? So the lab we're going to do right now, it's just to kind of really drive home that this is real. We are basically going to take distilled water and we have little dropper bottles. We'll add drop by drop strong acid. Then we'll add drop by drop strong base. What do we expect to happen to the pH as you drop in the acid?
Go down.
It's going to go down.
Well, no.
What about as we add in the strong base?
What?
Higher.
Probably come back up. So we'll do that. We'll see how it will actually get numbers to see how much does it move. And then we'll do the exact same thing, but instead we're going to just use a phosphate buffer. In the buffer, which is basically a weak acid, just like it's this, instead of the bicarbonate buffer, it's based on phosphoric acid, but it's the same basic idea. And we're going to do the same thing, add the same number of drops of the acids and base, and watch what happens to the pH. What do you expect to see when you add the acids and base to the buffer?
You'll need a lot more of it to create the same effect, or it won't happen at all.
Yeah, so you're going to add, because we're doing the same number of drops. So we'd expect if this buffer is doing its job, it's going to be, instead of letting the pH move like we saw with the distilled water, we're going to expect the pH to be kind of stabilized. And so we're going to see how it works. So this lab is, let's go to the blah, blah, blah. We're going to get back to the cyberloafing in a little bit. Whoops. La, 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 la. Here we go. All right, so we're doing the first part now, the buffer systems. Right here, here's the one. Here, this is actually the description of what we're doing in this lab with the phosphate buffer, but it's the same basic idea. The equilibrium moves back and forth. We're going to have a pH electrode. The pH meter is just a little thing that will read out pH. You've probably seen these in chemistry, unless you did chemistry online, in which case you've just seen pictures of them. And you're still just going to see pictures of them. You know, we're going to add drop by drop concentrated hydrochloric acid, mix, record what happens, then add concentrated sodium hydroxide, a strong base to the same beaker, and mix and read. Then when we're done, we're going to do the same thing, but in the phosphate buffer. So for this lab, I do want you to record the data in your lab notebook as we are doing this, just kind of like we did for the last class. So basically, you're going to want to paste in the instructions. And then it's going to make sense, you know, to make some kind of chart before we start. You know, you could say, like, you know, for distilled, let me do a different color. You know, we're going to start with distilled water. You know, this is going to be this, you know, drops, you know, pH. And again, the nice thing about having your thing made out of graph paper, it's really easy to make little charts. Is it 5? How many? Oh, it's really 6 drops, you know, and then you're going to add the base. Could do like 1, 2, 3, 4, 5, 6, I think 7. You know, so if you make a chart like this ahead of time, then you can just write the numbers down as you see them. You know, we're gonna actually, on the video, you're just gonna see Tina and I adding drops of acid and base to the beakers and mixing and reading on the pH meter. So as you get the number, the readout, you just write it in. If it's like 7.2, you can just write 7.2 and then wait for the next one and write, I don't know, whatever it is, blah, blah, blah. So what I would like you to do, as before you get started, make a chart. Make it. You're going to need one chart for the distilled water. You're going to need one for the doing the same thing in the buffer. And
So Professor, for the I did see that on the homework, like, or on this assignment on Canvas, there was the group, the class group data
right,
was available.
We'll get there later.
Okay, so this is separate though, because I already have that in here. So this is basically, you're saying you want us to create a chart because now we're going to watch it, and this would be like our observation compared to what the
Right.
class.
I should not have posted that thing ahead of time. Yeah, no, typically the way we're going to be doing this in real life starting next week is during the lab, we'll each get our individual data, and then we'll all type that into a group Excel sheet, which will then be shared, and then you'll have your data, but then the group data from everybody. So because we're doing this all online, you know, that's like the group data from a few years ago. So it would be like you would have other people's data, but I should not have published it. I should have waited. I didn't know people were going to be so, and it's cool that you were actually so on top of it. I think I'm more used to people not being that on top of it. So I figured no one would actually use it on anything yet. Right, so
I mean, I've got the instructions obviously pasted in, and then I had the class data as well as the chart that was in there with the class data.
right. So that's going to be more, yeah. So you're just going to have to like label it well as an appropriate figure and then be able to draw it, you know, bring it into your discussion.
Okay, yeah, because I mean, so
In the
okay.
future, it won't be an issue because we won't have the class data until everybody's done the experiment already. Again, that was just my bad. I should not have published that. So you can just make it make sense with how you refer to the graphs and stuff as you do your discussion.
Okay, yeah, that's kind of what I was thinking. I just didn't know if, like, for what we're about to do, if you wanted me to also do that version. Or like live one, I guess. Does that make sense? That's what I'm saying.
So
Like
pretend you don't have that yet.
Okay.
Yeah, pretend you do not have that.
Okay, so I'll still just do this as well, and I'll just label it and
Yeah, absolutely. You should be doing this right now. And everybody else is going to have the common class data to work with as well. But the first step is getting your own data. All right, so here we go. Share screen.
And we have one graph for the distilled water and then one graph for the buffer
Graph. You mean like
or
chart?
chart, I mean, yeah.
It depends. You know, there's no, as I think I've mentioned, there's no one right way to do it. There's probably lots of wrong ways to do it. But you know, if you had the same thing extended over and you did it neatly and said,
Mhm.
this is the distilled water and this is the buffer, you know, you could actually probably do it like that, right? So you could actually pH, distilled water pH, buffer pH.
Mhm.
So that would work out just fine too. Right, you could do one big mega chart, or you could do two smaller charts or whatever, as long as it's kind of clear. Right, does that make sense?
Yeah, I already made two, so I'm just gonna leave it like that.
Yeah, like I said, there's no right way to do it. There's lots of right ways to do it. It's all right. So here we go. I think that in fact, maybe before we start this, I'll mention one more time. People get really uncomfortable, I find, in this lab notebook thing because there is no right answer. And you've been so conditioned in school to jump through hoops and do it right and figure out what does the teacher expect and give them that. And like the lab notebook is a little like more free form. You know, you have to have the data in there clearly recorded, but exactly how you do it and how it's laid out, you know, there's lots of room for your personal style. And it doesn't have, you know, it has to be legible, but beyond legible, that's all that matters. It doesn't have to be super neat, or your graph doesn't, your chart doesn't have to be laid out with a ruler and, you know, looking like some, like, you know, I have some students who are just so precise and do everything and it looks like some crazy, like perfect, you know, model student or whatever. And other people, you know, looks more like my lab books, which are, again, they're legible, but they've got a little more character. You know, so there's no one way to do it. And again, if you do it and it's wrong, you just put an X out and you redo it. And that you don't lose points for not having been perfect. In fact, I expect you to not be perfect. I expect there to be things that are crossed out and rewritten or something, because that's what happens. You know, if everything is perfect, then it's usually a sign that it was like either copied off of something else, or you like did it all someplace else rather than did it in real time as you were actually doing the experiments. So please, as much as possible, try to find a place of, what is that, comfort in not being perfect. Because I think there's just been a lot of people get like a lot of reinforcement that they've done something just a little off, and then it's like spank, you know. So all right, so let's do this. Share screen. So the first, basically, there's going to be this first part is going to be kind of describing it as well as getting the data for the distilled water part. So that's going to be the first part here. So we're getting ready for getting our data, and you'll also get to listen to me just kind of yap a bit about the setup and stuff. So
Sorry, can I ask a question really quick?
for sure.
The last time we were like describing what you were doing the whole time. Are we doing that too with this?
No, because here there's not a, there's no, there's a good description of the actual methodology and the methods. So you
Okay,
know exactly what I'm doing. And the observations are just the measuring of the pH rather than some qualitative things of what does it look like.
okay. And so we're just entering the procedure into we just glue the procedure into the notebook and that's it for now? And then,
Yeah, so you should have the
the
procedure,
chart.
then like some little chart where you're
Okay.
getting your data.
Thank you.
And then you'll have the class data, which you'll get as that Excel sheet. And then you'll get to write up your discussion.
Okay, thank you.
All right, so here we go. All right, welcome to Virtual Lab.
All right, so we're going to do the chemistry lab today. And the exercise I'm going to demonstrate is we're going to investigate how pH is changing in a solution of water and a buffer as we add a strong acid known as hydrochloric acid, and followed with adding a strong base, sodium hydroxide. These are the pages that have the instructions, and it is totally okay for you to glue all of this into your lab notebook. Sometimes there is helpful kind of background information in the introduction. If I were a student, I would totally glue this in. All right, so we poured some water into these 150 ml beakers. And so a beaker isn't a very exact measurement device, but for this exercise, we just need approximately 100 milliliters. So it's more important that you have the same amount in both of the beakers. So I have 100 milliliters of distilled water in this one. And I poured some of this buffer, and so I poured 100 milliliters of buffer in here. So we're going to start off taking a look at how pH changes in this water as we add acids and bases. And so what I have here to measure with is a pH meter. So sometimes students are really gung-ho on starting and they start using this way, but you do need to remove the cap for this to work. And so if the pH meter is very off when you stick it into the distilled water, so distilled water should technically be pH 7. If it's completely off, you can go and do a calibration or ask your teacher to help you calibrate it. However, the main idea behind this experiment is not so much to be super exact, more showing what is happening when you add acid and base into water versus what's happening when you add acid and base into buffer. So it's more a relative comparison. So to turn this on, there's an on-off button. And so I have already turned this on. And then you dip the white probe into the water and it will blink, and it can take quite a while for it to stabilize. And so we'll wait about 30 seconds at the most. Oh, now we shut off. So I'm going to turn it on again. We'll wait 30 seconds, and then whatever it says after 30 seconds, you can record that into your lab notebook. All right, so in this case, my starting point is I'm going to record this pH.
So I edited this video to kind of have this cool inverse starburst when there's a value there that you need to pay attention to. So it's just this kind of like frame thing. And like she was saying, the value rarely ever just stops and stable. It's, so writing 7.53, or if it just shifted to 7.54 or 2, it just has to be close. What the differences we're going to be looking for are big. These little like changes as things are slowly drifting, that's irrelevant for what we're worried about. So this is going to be a value that you are going to record in your lab notebook.
What is the 71.9 underneath?
I think that's temperature. I think that's a little F of Fahrenheit thing there. All right, so we're going to continue
So-
on.
Sorry, I got a little bit disorganized getting my sheets and things. Do you still have that drawing that you made of the chart that we should be entering? Can you flash that really quick? Sorry to make you go back.
It's
Or is
just,
it too late? Okay.
you could make up your own chart even,
Okay.
right?
I think we're doing about 6 drops of acid and 7 drops of the base, if that helps.
Right, so do you, I should check in. I was assuming people
My
had,
lab book,
well,
this is my,
I was assuming people had, yeah, so there we have Sarah's got, how many people do not have any kind of chart written in their lab book right now? Raise your hand if you do not have a chart written in your lab book. Okay, so Maggie, you're the only one right here. So you should do it pretty quick, because otherwise I don't want to run out of time here.
Okay. Sorry, Sarah, can you show me your lab book one more time? I was messing around with my cutting and pasting. Thank you. I did 2 instead of 1. You can do 1 more column instead of 2 things. Okay, cool. Thank you.
The same
Sorry
day.
about that. Okay, I can go back.
All right, so here we're going to continue now. Take it away, Tina.
baseline. And so I'm just going to make a record of that. So I'm going to put 0 drops equals DI water, distilled water. And then I'm going to write down what the pH is. So that is my baseline. Note that I have also already made a table to put my data in. This is really important. It's good practice because one, sometimes you don't have time to write this as you go along. And 2, this makes a lot of sense because it shows you and me that you have read the procedures, you understand the procedures, you know what to do. And so I have a column here for my water beaker and I have a column here for my buffer beaker. I have indicated that I'm going to add 5 drops of acid to the water, and then I'm going to continue with adding 6 drops of sodium hydroxide base. Then we're going to repeat the whole experiment with the buffer, and so I have another table written out there ready to go. All I need to do is record my pH on the meter. So in this exercise and in this video, we want you to record whatever the pH meter is saying into your lab book at home. So at this point, we're ready to go. I'm going to put this probe gently. Sometimes pH probes are very sensitive, so always handle any equipment gently. And then we're going to start off with our acid. So here, I'm going to add 1 drop. And I'm going to stir. And then we're going to see what the pH is. And we'll wait a little while. And then I'm going to record in my lab notebook.
Right, like I said, whoops, shoot. It usually doesn't totally stabilize, it kind of drifts. So any of those numbers in that little period while the kind of starburst is around there is fine. Notice the big, it's huge difference. The difference going from, we just dropped by over 1,000, in terms of the concentration of hydrogen. That's what's important. Not drop, we went up. We dropped the pH number, we increased the concentration of H+ by over 1,000. Like the little fraction down here drifting is irrelevant for the take-home message that we're looking at right now. So you want to have to, and if this is going and you need to go back, these are all online, so you can, look at these after class as well. These videos are just part of the module for the chemistry review lab on the Canvas site.
I'm gonna put it here. So second drop. Stir. And we'll measure. And record.
Right, so again, you would normally be doing this for real in the class, but instead, this is still giving you a sense.
We'll add our third drop. Stir. And measure. And record.
So you can see a number there.
Our fourth drop. And
You can see it there. Reflection, that's better. Right, and again, if you wrote 2.19 or 2.22, it doesn't matter for this lab. Those are pretty much the same, given the bigger swings that we actually care about.
And I'm on my last fifth drop. All right. And record in your notebook.
Right, so what happens as she added acid to the water?
pH went down.
pH went down, right? Because you increasing the amount of the concentration of H plus, the pH goes down. Was it a kind of linear? Did each drop?
No,
No.
her rate starts to decrease. Her rate of descent starts to decrease.
Right, and it's kind of interesting when you think about, like, if let me back. If you think about, let's say each drop again was 1,000 H pluses, right? And let's say in my beaker to start, there were 10 H pluses. Now the first drop would go from 10 to 1,000. That would be increasing by 10 to the third. So pH would go down by 3, right? But if I add the second drop, so this went from 10 to, like, I should say 1,010. The next drop would go from 1,010 to 2,010. If I added another drop. Now, instead of going up by 1,000, I've only gone up doubled it. I've only gone up by 2, right? So if I am adding just this linear, the same amount of H pluses with every drop, each drop is going to have even less of a overall increase in terms of how many times did we increase the amount of H plus. So it makes sense that the first drops are going to have a very large effect on pH, and the subsequent drops are going to have much less of a change in pH. Does that make sense? Because it's not just like how many more in a linear fashion are we adding? It's how many times have we multiplied the concentration? So anyway, let's get back to our thing here. All right, so now she's going to start adding the base, the sodium hydroxide. And again, it's adding to the same beaker.
Next, we're gonna switch to our sodium hydroxide, which is a strong base. And I'm gonna add 6 drops, but 1 at a time. So drop 1. Looks like I got 2 drops there, so I might actually have to skip that data. But the thing is that we're collecting class data. And so my data, even though I don't have a drop 1, I'm gonna drop 2. I'm gonna just put a dash in my data, but because all the other groups have data, chances are that they didn't do 2 drops there. And so we can average these numbers together.
So that's important. Did you notice she accidentally got 2 drops? So she doesn't have data for 1 drop, which means you can't pretend, because you are going to be looking at this data for real, and you're looking at the data average with everybody else's data. So you can't just like pretend it didn't happen and just write down what you saw. You need to, true and honest, put a little mark like, I don't have data for drop 1 of the base. The value we're going to measure now is actually going to be for 2 drops of base. And then we can continue on and with 3, 4 as we add more drops. But yeah, make sure in your lab notebook, if you wrote down a value for 1 drop of base in the water, you're making that up because we don't have data for that. Right. So here we go.
In our spreadsheet. And so for my drop 2 then, I'm going to record and then I'm going to add drop 3. And drop 4.
Again, you can see it coming up, not necessarily dramatically, because it's kind of the same kind of idea. There's gonna be some tipping point where all of a sudden the proportions are gonna change more dramatically.
Drop 5.
Right, so you might expect drop 5 that it should go back exactly to where we started. And it's not exactly, it's a little lower. Was off a little bit. So there's been, at this point, there's been a little less H pluses than H hydroxyls that have gone as opposed to the H pluses that went in. What's another possibility?
Human error, so just like the size of the drop.
Yeah, maybe.
Yeah, size of the drop. The size of the drop is, a drop is pretty close in terms of uniformity of volume, but it's not exact. So the chances are 5 drops of the strong acid, there was a little bit more volume than 5 drops of the strong base. What do we expect now, though, if we're right on the cusp when we add in our next drop of base?
A larger swing in pH.
Yeah, so let's see what happens.
And my last drop.
Right. Oh. So now not only have we gone up, but we've overswung because now we actually have a greater amount of base that's been added than the original acid that was added. Right. So this should make you feel pretty confident that things are working the way we would predict. And let's finish this up.
And record. Okay. So now I'm going to switch to buffer. So I'm going to clean off the probe. Just rinse it off. Make sure we're not having any residues to influence our data in any way. And we're going to switch to our phosphate buffer.
All right, so what happens when you add strong acids and bases to distilled water?
It changes the number of hydrogen ions that are in that water,
And
either up or down.
how is the pH?
pH, well, the more acid you add, the pH decreases. The more base you add, the pH increases.
And how would you describe the change in pH? Like, was it like pretty mellow or kind of extreme?
It's an extreme in the beginning and then it's subtle thereafter.
But it just a little bit of acid made the pH really low. Then you added more. It's pretty labile. It's pretty easy to get it to swing low or swing high. And like I said, you want to have the pH really stable in your body. pH has to be around 7.4. If pH goes below 7 or above 7.8, it's actually no longer compatible with life. So you really have to rein in the pH range in order to stay happy and healthy and alive. And like I said, the first defense against pH change is going to be buffers. So let's see what happens. We're going to do the exact same format, the exact same procedure, except instead of dropping the drops of acid and base into water, we're going to put it into a phosphate buffer. And we're going to see and compare. So let's do that now.
So I've got my essay written and I've been working.
Stupid Grammarly guy. Well, I'm sorry. That's driving me crazy. Yeah, it kind of pisses me off that they're getting money off of the videos that we made. We don't get anything from this. That's ridiculous. All right, I'm going to mute this dude till he's done. And they're not even real. They're all actors. It's like he's not writing a paper. He's like pretending to write a paper and then claiming this thing is really good for him. And he's just getting paid to, like, you know, try to sell you something. It's not even real.
I think they're going to force you to listen to it because it looks like it's, oh, there you go.
If you set up your account appropriately by them showing ads, you do actually get residuals.
What's that?
If you set up your account, your YouTube account, you can actually get ad money off of that.
But
So
they probably push even more ads into them, I'd
it's
imagine.
actually not that bad. I used to work in this, so I'm just saying, you
We
could make money off that.
I'll talk to you offline about that, because yeah, because it kind of bums me out that my students have to get those ads piss me off. So I feel bad knowing that students have to get subjected to them as well, trying to watch the videos I post. All right, here we go. So here's Tina doing the exact same procedure, but with phosphate buffer. So you know the drill here.
All right, so next we're gonna investigate how the pH is affected when we're adding the acid and the bases into a buffer. And so this is a phosphate buffer, and we'll need to get our baseline first. And so we're gonna get our baseline reading. I'm gonna record that into my lab notebook. All right, it's a little lower than it should, but as I said, we're trying to demonstrate more a relative relationship and compare the two fluids.
Right, so it's supposed to be mixed to be a 7 pH 7 buffer, and obviously it's not quite, but or it could be the pH meter's not quite calibrated, but either way, that's not what matters. What matters is to see how things change as we add acids and bases to this buffer. So we're going to start here somewhere around 6.4, and now let's start adding some hydrochloric acid.
So I'm going to record this now. And then we're going to start our experiment. And once again, we're going to start with the strong acid. So I'm going to add 1 drop. I'm going to stir. I'm going to measure. And I'm going to record. I'm going to add another drop. And record. We'll add another drop. This is drop 3. Right.
So we got drop 3 of, so you're probably know by drop 3 with the water, it had already like dropped down by 3 pH numbers. Here we see it's staying awfully close to the initial reading here. It's shifting a little bit, but not very much.
And record. We're going to add our drop 4. And measure. And record. And this will be the last 5th drop of acid. And measure.
Right, see that? This is 5 drops of acid and it's gone down like 0.05 pH units, right? So this buffer is really, really helping. You know, with the other, with pure water, we went from like pH 7 down to pH 3 or something. So let's watch what happens when we add the base. Now, instead of adding acid, we're going to add the hydroxyls and see if we can bring the pH up.
And record. And now we're going to switch and we're going to start adding our sodium hydroxide, the base, drop 1. And measure. And record. Drop 2. And measure. And record.
It says it's barely moving at all.
And drop 3. And record. Drop 4.
Drop 4. Couple of more drops. We're going to be done.
And record. Drop 5. Record. And our last drop of base. Last measurement. All right, and so next you're gonna go over to the computer in our lab and we're gonna enter your group data into our Excel spreadsheet. And then your instructor would upload the whole Excel sheet to Canvas, and so you can graph things and draw conclusions based on the data you see from this data. Last note, when you're adding acid and base together, you make water and salt. So when you're disposing of this, you can pour it down the sink. And finally, because these are strong acids and strong bases, you must wear gloves and safety goggles to protect your eyes.
Oh, what is this guy's got? What's he doing there?
You ever wondered what actors and actresses do when they have to get in shape really fast?
No. All right. Oh my God. So
That was amazing on every level.
that was just jarring.
Agreed.
Okay, so what we have just done here is you didn't get to do it yourself, but at least you sat through this process of really getting a sense of, oh, buffers are doing something real and observable and intense. For the class, you're not going to need to get so much into detail about how buffers do what they do. I think it's useful to think about the adjusting of the equilibrium, the shifting of the equilibrium of the weak acids and bases. But don't get too caught up in the mechanism of it, but you definitely need to understand what it is doing and why it is so critical to the functioning of the body. The idea of buffers, resisting resisting changes in pH and how important that is in maintaining your pH homeostasis, making sure that your proteins aren't going to all get denatured and misshapen and mess up their functioning and all that. So for this lab and for most of the other labs, you'll get your own data, but then we always assume that, something, maybe you got a one-off thing, or maybe you did something wrong, or is what you got typical? So you don't usually, you do it yourself is interesting, but if lots of people do the same thing and they all get the same answer, then you start trusting a little more that what you saw and what the overall trends that you're seeing are actually real, that they're not just due to this randomness. So for this lab and for most labs, after you get your own data, you'll type it into a spreadsheet on the computer in the classroom, which will then get uploaded to Canvas, which then you will have to integrate into your write-up as well. So you'll have your own personal data, and then you will also, I'll show you how this works. It says, here is the Excel file that includes the class data. So we click on this. In fact, I'm going to just download it as a Excel. Looking at these through the previews with the web browsers, you only get a, let me say, I should probably say this. When you are looking at Excel spreadsheets through your browser, you are not getting the full experience of the Excel spreadsheet. It kind of is designed just to kind of let you have some sense of what the file is, but you don't have a lot of the details, and the graphs are all weird. And don't print out your Excel spreadsheets from your web browser. You need to download them as a file and then open them up in Excel as a program. And you all have access to that through there's a thing, I think, in Unit 0 where shows you how as a student you can get all the free Microsoft Office stuff. So when you are going to get one of these files, make sure you download this thing and then open it. It's going to open up within the actual Excel program rather than in the web browser. So then you'll have full access to the content of the file and all of the ways of viewing it and analyzing it. And so so this is a thing, when you download it off of Canvas, this is what you're gonna get. This is showing there were like 4 different groups. This is acid drops, base drops. This line here is on average. You can see on average, they started at 7. It went down on average. This class, it went down as low as 1.4 after 5 drops, and then came back up almost to like 11.1 by the end of the 6 drops. Whereas in the buffer, you can see it started at 7 on average. Lowest it got was 6.6. The highest it got was 6.8. So this is really nice to see the change. Like when you are writing your discussion should include what you've personally recorded, what you saw in your group, which was what you just did on the video. But then you always want to put it into the context of the greater class. So you can say, ours went down and up in by this amount, and this was, this behavior was reflected on the class averages and you want to use numbers. Don't just say like it went a lot or a little. Like what does that mean? A lot or a little compared to what? What is it means to you might mean different to me. Here we can see that we had like the pH shifted from 1.4 to 1.11 over the course of adding the acid and the drop. There was a range of pH values of like almost 11, which is huge. With the buffer, the range went from minimum of 6.6 to 7. The range was like less than half of a pH unit. So we in the distilled water, the pH swung over 11 pH units, which is, we talked about 11 orders of magnitude. That is, oh my God, 11, that is 100 billion times difference in the amount of hydrogens in the water. Whereas with the buffer, the pH didn't change even like, a factor of 10 or something. So use numbers, and you always want to have your graphs labeled. Like you'll print this out and you'll paste it in and make sure you write like, oh, this is figure 1. So then in your discussion, you can say, as we see in figure 1, in the class averages, we had this crazy wide range of pH from 1.5 to 11, yet the buffer had a very tight, pH was held tightly, within this range of around 0.4. So you want to use this graph labeled specifically with some graph numbers. So in your words, in your discussion, we can see where these numbers are coming from. And also graphs should never be orphaned. There shouldn't just like, it's there, let's tape it in my graph in my lab and I'm done. It's like, this has to be used to support your discussion. Just to get you a sense of why the pH looks like it's going in this weird direction. It looks like it's really it's going from 7 to 3 to 2 to 1 to 1.4. I made a graph here where I just said, okay, here was the pH that we measured. This is H+ concentration. It's just 10 to the pH minus. So it would just give us back H+. If I look at H+, it's actually going up quite linearly as you're adding drop by drop by drop, right? So if you look at actual H+ concentration, it's going up pretty linearly, even though the pH number itself is doing this, right? So just to kind of, just because pH is moving in this way that doesn't seem linearly drop by drop, the actual H+ concentration actually was going up fairly linearly. The dropping, I'm not quite sure what the heck happened over here, but that's life. Sometimes things get weird. So any questions about that?
I have a question. Just below the experimental procedures for the part we just did, there's just a question says like, how did your observation of pH change? Can we just answer that question in our discussion conclusion, or do you want that like
Absolutely.
separate? Okay.
No. So a lot of times those little questions are just things to jog you to think about, make sure this is something that you are covering in your discussion.
Perfect. Thank you.
And so remember the discussion, you're going to have your data, the class data, and then you have to kind of put it together. Like, what does this mean? What does this mean in terms of demonstrating what buffers do and how this really shows in real life what's going on? What is this evidence? And why is it important? Why are we even talking about it? How is this related to physiology? That would make sense to put in your discussion. Again, it's not a term paper, but it should have kind of the basics of how the data that we gathered is actually telling us something interesting, kind of interpreting what it means and talking a little more about the concepts that are being demonstrated here. So that all makes sense? All right, so before Thursday, what I would like you to do, the jumping lab is a lab where you actually are supposed to do this kind of pre-lab. The pre-lab is really easy. If you spend more than 10 minutes on the pre-lab, you're doing too much. So let's talk about pre-lab. The jumping lab. Oh, well, actually, that's not the one I wanted to do. So obviously, give yourself a little room in your lab notebook to tape in the class data for the pH and some space to do a little discussion. But then you're gonna do this jumping lab. All we're gonna do for today, or for the before Thursday, is this pre-lab. All it needs is the objective. Again, which is like a sentence. How do the independent variables affect the dependent variables? Hypothesis. What you think the answer is going to be and why. Sources of variability. What things might be affecting the dependent variable that we are not measuring, that we should probably just keep in the back of our mind. So I don't know if you all remember the jumping lab. The jumping lab, we are measuring these body measurements. There's going to be like calf circumference, weight, and height. And then we're going to look at their vertical jump. So what is going to be the independent and dependent variables in this lab?
The independent variables are going to be the calf circumference, the weight, and the height.
Exactly. We have basically three. These are like our independent variables. We'll look at people with different values of calf circumference, weight, height. And then we're going to look for correlations. Do any of those correlate, seem to have a relationship with the height of their vertical jump? Right, this is going to be our dependent variable. Let's see what might affect their vertical jump. What would be sources of variability? What kind of things might affect their vertical jump that aren't one of these measured variables?
Maybe how often someone exercises.
Yeah, kind of their basic conditioning. Absolutely.
Age.
Maybe age.
About the surface of the surface they're jumping off of.
Absolutely. If they're like in some, gymnastic spring floor versus sand versus, the surface they're jumping would make a huge difference. What else?
Their form.
The form, how you jump. Are you just kind of trying to jump? Or are you doing the Russian lift with throwing your arms back or throwing your arms up? Or it makes a huge difference what kind of form you use. What other things? Part of the reason you come up with this ahead of time is you try to control for them before you do the experiment so they don't ruin your data. For form, we're going to make sure everybody does the jump exactly the same. There is a very tightly specified form of the jump. Everybody has to learn how to do the jump and how practice it a bit. So minimally, everybody's using the same form. Everyone's going to be jumping off of the same kind of surface. What are other things that could affect the dependent variable, the vertical jump?
Their level of energy.
Level of energy. That one's going to be a little harder because some people are going to not slept enough, or some people have just eaten some Adderall before they came to class or something. It's so some things.
I was going to say, like, how many times they jumped before you're recording.
Right,
Like,
so,
is it your first jump, second jump?
and every jump's a little different. So we're going to have them. That's another source of variability, is every time you jump, it's a little different. So we're going to have do 3 jumps and average them to get kind of a average. And give people a chance to practice a little bit so they get a feel for what it's like. What are other things?
The source of variability is the dependent variable.
No. It's things that might affect the dependent variable that aren't our independent variables. So things other than this that might actually affect this. So we need to think about them because they could mess up our results if we're not careful. What are other sources of variability?
Muscle fiber type or composition.
Yeah, actually just the genetics of whether you have more fast twitch or slow twitch is going to actually probably make a difference in explosive movements like a jump like this.
Maybe somebody did a hard stair workout yesterday and their calves are really tight and sore.
Yeah, that kind of stuff as well. Or just damage. Like we have to, in fact, one of the things we talk about exclusionary criteria. These are the criteria that would exclude someone from being a subject in our experiment. If somebody has like blown out knees and they can barely move, that's going to be more important about their vertical jump than any of this other stuff. So, just their basic, injuries would be a source of variability. And we would want to say, okay, if somebody has an injury that really affects their ability to jump, they shouldn't be doing the experiment because that's gonna totally swamp out any effect from our independent variables. Shoes, what kind of shoes? If you're wearing some Air Jordans or wearing some Birkenstocks when you try to jump, that's gonna really affect your ability to jump. And that's something we can try to take care of. We actually have everybody jump shoeless. Everybody takes their shoes off. So that's a source of variability that we don't have to worry about. So that's why we think about this ahead of time. If we can think of things that might affect the dependent variable and kind of hide the effects of our independent variable, if we can control for them ahead of time, then it's good. If we don't control for them ahead of time, that source of variability, if we didn't think about the shoes probably matter so much that the shoes probably are going to completely make all our data useless, because some people were wearing sandals, some people were wearing basketball shoes, and that really made more of an effect on their jump than this other stuff. So think about, and your hypothesis, there's no, what's a possible, in fact, we are kind of done. Just before we leave, I'll just give a little more, what would be a hypothesis? A possible, there's no right hypothesis.
Someone that weighs less, that is tall with larger calf circumference is going to jump the highest.
Right, and that's going to get,
those would be our higher end of things.
Right, and I would say you might want to focus on one, or you can focus on a few of them, but be careful about making it too complicated. And you need to have a why, right? So you have to have the what and the why. So your prediction and why. So somebody who weighs, there'll be, so you say like an inverse correlation with weight. And why would you expect that?
Because gravity is going to make it harder for heavier people to jump higher.
Exactly. So you could say, I predict people who are lighter will be able to jump higher because they have less to fight against gravity. But I could also say people who are heavier probably have more muscle mass and will likely be able to fight gravity more and jump higher, right? So either of those hypotheses are completely fine. You could either say weight is inversely correlated with jump height because you have less to fight against gravity, or weight is directly correlated with jump height because that's probably related to more muscle mass, so you can launch with more force against gravity. There's no right answer. There's no right hypothesis. But it needs to have a prediction and a why. I mean, one of the things that we add into this is this idea of BMI, which is a ratio of height to weight.
Professor, I have gotta go. I have a 12:40 class, so
Okay, so
I'm gonna say bye.
okay, I will, yeah, sorry for going to, yeah, so BMI is, but and I'll record the end of this. I'll see, you can look at this on the YouTube tonight, but it's basically just saying BMI is an index that is a way to get around just thinking about weight without other context. So, and in the lab book, it talks about it as well. So, yeah. Yeah, normally I try not to go this long. So I will, but since I'm doing it, I'm going to just say BMI in general, there's BMI. If you calculate it out and it's between 18 and 25, this is what we'd call kind of like normal or healthy, where your ratio of your height to your weight is kind of normal. You're probably like in reasonable shape. If your BMI is greater than 25, this is becoming like overweight, meaning you weigh a lot for your height on average. If it's greater than 30, we've gotten what's called obese. If you're less than this, then it's also unhealthy. This is kind of you're too scrawny. Like you don't weigh enough for your height. You might be anorexic or something. You know, in reality, this is kind of a rule of thumb. If you really want to get somebody's like amount of fat in their body, there's much more accurate ways to do it. There's underwater weighing and bod pods and caliper measurements and all this stuff. But the fact is BMI, so you could say, you know, people in the healthy BMI range will jump better than someone with unhealthy BMI, or calf, you know, calf circumference. Calf circumference might have to do with their muscle in their leg, but the calf circumference could be fat or muscle. So maybe calf circumference is positively correlated with jumping higher, but only if you have a healthy BMI, because then that large calf is probably due to muscle and not due to fat, right? So there's lots of ways you can play with your hypotheses. So, and again, there is no right answer. And as we continue analyzing the data, you'll look at lots of things beyond just your hypothesis, but for Thursday, have at least a hypothesis. So I'm going to stop talking.